In progress.
Hey there, everybody. Welcome back. It's good to see y'all again. We are going to continue on with our course in college algebra. We're at 3/4 of the way through approximately. We got 2 chapters left. I'd say approximately 3/4 of the way because not all the chapters have the same number of sections. We have 12 sections left out of 50, so we are 3/4 of the way. How about them apples? All right, chapter 7 is on systems of equations. Systems of equations have more than one equation to solve simultaneously. More than one equation that needs to be solved simultaneously. Simultaneously. Let's just rewrite that word. Simultaneously. There we go. Which means a solution for a system satisfies each equation. Okay, that's what a system of equation is. There's more than one equation. We'll be working with 2 primarily. There's cases where there's 3, 4, 5, 6, a lot. My graduate work had, I think, 8 or 9. My graduate work was ugly. You wouldn't like it if you saw it. You'd be like, whoa, he's a crackhead. All right, a solution for a system satisfies each equation. We're going to take a look. We're going to start with 7.1, and we're going to do solving systems by graphing. All right. So when we look at solutions graphically, for a linear equation, or for any equation, but for an equation, the solution must fall on the line. Must be on the line. Okay. So what do you think has to happen? What must occur for a system of 2 equations to have a solution that works for both of them? Think about that for a second. Just think about it. Maybe draw some pictures. Now, yeah, okay, let's draw some pictures. Here's some parallel lines. Do they have a solution that is shared? Okay, these are our parallel. That's supposed to be parallel. They don't look all that parallel. They look like they're curving together. Maybe let me make it a little straighter. There we go. Now, let's say I have a solution A. It's over here. Is it on both lines? No, it isn't. I have a solution B over here. Is it on both lines? No, it isn't. For a system of equations to work, the lines must intersect. So if this is line 1, and this is line 2, and that's our system, this point right here is our solution. So there's one solution here. This has no solutions. There's one other way that a system of equations can end up resulting. I could have line 1 here, and then line 2 happens to fall right on top of it. So that A, B, C, all the points on either line satisfy it. Here, there's an infinite number of solutions along the line. So 0 solution, 1 solution, and infinite solutions for lines. All right. When we have one point of intersection, here's some terminology for you. I'm not big on the terminology because it doesn't make me think of anything. If you're going to be a pure mathematician, it's pretty important, but I don't use these words very often. And I do math a lot. This is said to be a consistent system when there's only one solution. And no solutions is inconsistent. Infinite solutions, the system is said to be dependent. It's a dependent system. There's some fancy math jargon for you, more for Jeopardy with grandma, grandpa. Or the whole family. I don't know why I say grandma and grandpa. I never watched Jeopardy with my own grandparents. So I don't know where that came from. Oh, that's good. All right, so when we do it graphically, there is a problem. One problem with graphical solutions. It can be really hard to get the exact solution. And so often this ends up being an estimate at best. Well, I'm going to say estimate at worst. Because sometimes it's easy. If it falls on you can tell it crosses at the origin or something like that. But it is error prone since we have to oftentimes guess where they're crossing to a decimal place or two. This is an error prone path. Error prone. But it does work wonderfully as a backup for the other systems that we're going to do. Substitution and elimination, you can see over here on the left. So let's take a look at a couple. First one we'll do. 7x plus 2y equals negative 13. And x minus 2y equals 11. So I think to graph these, I will get a slope-intercept method. So if I subtract 7x, and if I divide by 2, I get negative 7 halves x minus 13 halves, or negative 3.5x minus 6.5. If I do this one, subtract x, we've got negative 2y equals negative x plus 11. Divide by negative 2. Y equals 1/2 x minus 11 halves. And this is y equals 1/2 x minus 5 1/2. So if I were to do this graphically, oh, I'm already not liking it. My intercepts don't look good. One, two, three, 4, 5, 6, 7, 8, 9, 10. All right, I got my x-axis, my y-axis. I will do this line here in red. It starts at negative 6.5, which is between 6 and 7, negative 7, right there. And I think it might be easier to do a rise of 7 and treat this as 7 over negative 2 for the slope. So I'm going to go up 7. This was 6.5, that's 7, and then I'll go left 2. And I can go up another 7. Let's see. 1, 2, 3, 4, 5, 6, 7. And I'm there, and I gotta go. Wait a second. I'm there, and I gotta go left another 2. Right there. So that's line 1. And I wrote this in green, so we'll do this one in green. Negative 5.5 is right there. It almost looks like it's crossing it, but it isn't. Up 1 over 2. And then down 1 over 2. It's close. The intersection is close. To 0 and negative 5.5, but it looks like it's a little to the left and down a little bit. If we do this in Desmos, we can see exactly where they do cross. I'll zoom in on right there. See, my graph's a little off. They are so the actual solution from Desmos negative 0.25, negative 5.625, which is negative 1/4 and negative 5 5/8. So a little to the left and a little down from 0, negative 5.5. So that's my error estimate. And this is the actual. So graphing it can be pretty hard to get the exact solution unless you're using a graphing calculator. And let's be honest, most of the data you look at for answers and stuff isn't produced by you. So you don't have the equations or anything. You just got to look at it. And so you're estimating where the answer is. That's why I was saying that it's error prone and not the best method. We'll learn better shortly. But we'll do a couple more like this so you can get a feel for it. We can do x plus y equals 0 and 3x plus y equals -4. So if I solve for y, I get y equals -x. And if I solve for y here, I get y equals -3x minus 4. I have no idea where these are going to cross. They're both downward. That one looks kind of like that. And that one looks kind of like that. So I'm guessing we're going to be in this second quadrant. This quadrant right here. I think we're going to be here. And I think we're going to be close to the origin. But we'll find out. 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, 5. All right, equation 1 in red starts at the origin. The y-intercept is 0, and it has a slope of -1. So that's L1. And L2 is negative, intercept is -4. We have slope is -3, which is -3 over 1. I'm going to treat this as 3 over -1. So I can go up 3 and back 1. Up 3 and back 1. Is that -2 too? That looks like -2 too. It looks like I hit a dot I already had. We go check on Desmos again. That's a pretty handy method of looking. This is not something you should be doing on a test. This is cheating. It's very much cheating. You're better off being wrong and making a mistake and learning the hard way. But if you're not doing it, it's a great learning tool. It is. It's -2 too. So it meets exactly at an intersection that I hit while I was doing rise over run. So that one was easier to spot. Okay. That's the idea of doing this. Let's see. Let's do another one. This is number 24 from the homework. 6y equals 2x minus 12, and x minus 3y equals 6. So I'll do this one first because it's right here. I will subtract x, and I get -3y equals -x plus 6. And I divide by -3, and I get y equals 1/3 x minus 2. If I do that here, I divide by 6, get y equals 2/6x minus 12/6, which is 1/3 x minus 2. We got the same line. So this is a scenario where line 1, rather than sketching it fully, I'm going to just estimate it. We're down to rise 1, run 3. That's line 1. And then line 2, I drive straight over that thing. Line 2 is also there. So this has infinite solutions along the line. There we go. All right. Let's do one more. Why don't you guys give this one a try? Now that you've seen what's going on, a few ones. 2x minus y equals 3, and negative 4x plus 2y equals 12. All right, I will assume you did. Here it's easier to find y by, I got 2x minus y equals 3. I will add y to both sides and subtract 3 to both sides. And I get 2x minus 3 equals y. Here I will add 4x to both sides. I'll do this in blue or green. And I get 2y equals 4x plus 12. And I will divide by 2. And I get y equals 2x plus 6. X and y. Throw some arrowheads on the axes. All right, the red one, 2x minus 3. The intercept is right here, 0, negative 3. We go rise of 2, run of 1. Rise of 2, run of 1. Rise of 2, run of 1. And the green one, rise of 2, run of 1. Rise of 2, run of 1. Now, graphically, these look parallel, and I can see from their slope, they are parallel. So these are parallel lines like railroad tracks. So this system has no solution. All right, that's it for 7.1. Peace.